Okay.
Rachel, she had a D.
It's supposed to be a sig.
Oh, sorry, we're supposed to pay attention now.
Maybe you should get a starter gun. I know where
A
this
starter.
Lockdown.
Yeah, no kidding.
Intruder.
Intruder alert, Mr. Clark.
All right.
Take him down.
Well, they did. The intruder did come to my room yesterday. Did you guys hear? Were you in there?
We were right over
414. It's like
Oh no.
started shaking the door. Yeah, started trying to get in.
Was that scary or what?
I was standing right by the door. I took a couple of
I knew he came through the door. We were in room 412. And we screwed like someone was like I was not awake.
All right. So let's do this. There isn't a whole lot new, really. I mean, threw a lot at you yesterday.
Let's all review.
And so,
part of that.
hopefully,
Yeah.
we'll have a decent amount, I think, of some work time. We haven't for a few days here. So give you some time to work together here and work on some of these problems, ask questions if you need to. So first thing I want to do, so we'll go over a few of them here, and then you'll have some more of kind of the same kinds of things for homework for Monday. So you'll get another chance to get at these kind of problems and maybe feel a little better about it. So let me go through, and I'll put these notes here up on the website where I do the assignments, okay, under today's thing. So if you don't want to try to jot this down real fast, but I'm going to zip through it here pretty quickly. Just again, the things I put up there, the things that we were going to talk about, or what would be on the next quiz. One of them was the chart stuff, and then two of them, chart stuff and the global max min stuff. And what I've done here is kind of tried to show you how the two are kind of related and how they're a little bit different as well. Global max min versus like local max min and that stuff. And so what I showed over here is I just made up a function with some local max and inflection points and stuff like that. And so if you were being asked about those kind of questions, where's the function increasing, decreasing, concavity, all those things that are in the chart, right? Basically, you do the derivative, set it equal to 0, right? And you put those points, and that would be here and here and here, right? So you would have an equation. What I didn't show here is it'd be an equation. So you'd use your derivative rules, right, to find your derivative, set it equal to 0, put those on a number line, check numbers in between. In this case, obviously this graph's going up, then down, so that the derivative would be positive, then negative, then positive, then negative, so you get this kind of thing. So the number line would tell you your local max, local min, increasing, decreasing, all that stuff. Your second derivative, then, you would do that derivative again, set it equal to 0, find those points. In this case, it would be here and here, right? Those are possible inflection points. And these might be pi numbers if it was a trig equation, right? I just made one up here. But if it was a trig equation, you set it equal to 0, these could be like pi halves and 3 pi halves or whatever, like ones we've done. But this tells you the graph is concave down, concave up, concave down, which of course you can see. Now, you know in the problems we're doing, since we're using equations, we're not going to have the graph. You won't be looking at the graph, especially on the no calculator one. And you won't be looking at the graph, you know, even if it's a calculator one, but if it's a global max min, you're probably not going to take the time to graph it. To be honest, I think that's typically a waste of time because you got to do all the work with the equation anyway. So you won't be looking at this, but you know, visually in your head, you might be thinking, okay, I'm working with this equation, but I'm looking for local maxes, and I'm looking for inflection points, and I'm looking for where its highest and lowest points are. So, you know there's a graph out there somewhere for this thing, and that's what you're finding, right? But this is the work you're doing, telling you where those things are, okay? Now, if you're looking for a global max min, now what you're really looking for is this highest point, and you're looking for the lowest point. Right? And which happens to be there. Well, where can the highest and lowest points be? Well, it's either got to be at a local max, like this one, or it's got to be at an endpoint, like the minimum over here. Right? And now if this graph hadn't went all the way down there, maybe this would have been the minimum. Or if this would have went back down here, maybe. Or something. But what we said yesterday is your candidates, the places to look for a highest and lowest point, is where the derivative is 0, your stationary points, or at your endpoints, okay? In this case, our function is defined to be from 1 to 7. So what would we do? We'd find out where the derivative is 0, so you'd have your equation just like you did here. You'd find out where the derivative is 0, which is at 2, 4, and 6, right? Which you would find through work with your equation. And your endpoints are 1 and 7. So you would take all those and you'd plug them in where? To find the highest point, plug them into the original function f, because you want to know those y values. And you plug, and you want to know the lowest point. So you would take 2, 4, 6, 1, and 7, and you'd plug them in. You do your list of candidates like we did yesterday, and you would plug those into your f equation, whatever that was. And if this was actually the picture, then when you plugged in a 2, you would get the biggest value. And when you plugged in a 7, that would be the smallest of all these values, right? And that's what we would do. Okay, so that just kind of summarizes what you would do. But now understand, when you look at this, I've given it to you as a picture because I want you to visualize, what's going on. But you would have equations instead that you'd be working with, right? But this is the process. So there's some similarities in the sense that you find the derivative set it equals 0 in both cases. But what you're after is a little different in each case. Local maximum versus global maximum. Okay? So that's going to be a big part of the quiz. I would say half the points probably, roughly, on the quiz come from those kind of problems right there. Okay? All right. Then we got into this thing with differential equations yesterday, right? And maybe a third of the points come from this then, right? This is probably the other, not quite half the quiz, but another good chunk of the quiz. So we had 3 types, and we wrote that down. There are the types we can do with a simple antiderivative, like 6x minus 5. And the key was if it just has the input variable, like x or t in there, you can do an antiderivative. But that's going to be a very small part. We're probably not going to have you do much antiderivative. Did you have to do any antiderivatives on the homework? Were there any? I don't think there were. I don't think there were any you were supposed to do an antiderivative. So if you did, you were reading it wrong. I don't think you were supposed to. I might be wrong. Maybe there was something, but I didn't think there was. Then there's this one we can't solve yet, but we're just going to memorize the solution. That's the one that looks like this. Now, that's a very specific one. That's an exponential function. It's usually going to have to do with bank interest or population growth or something like that. It's a very specific situation. Okay? And you had a problem that talked about a little bank interest, and that's where you were supposed to use this formula. That was number 47, I believe. 47 on that one page. Okay? And that's that one. And then there's a kind we can't really solve, but we can verify that something is a solution. And that's the big thing that you're going to have to do when it comes to differential equations on this quiz, is be able to verify that something is a solution. Okay? And so here I've done an example. This is the one we worked out in class yesterday, I think. Y prime equals 1 over 2y. Is this a solution? Now, the biggest question people that came in this morning, and I appreciate those people coming in this morning that were asking some of those questions, because it was really helping you get that straight in your mind. Because the problem is you have these 2 equations. I talked about this t-chart. Well, where do you do the t-chart? Well, and I wrote it here, but I also have it up here. Remember my example from 5th grade. Okay, you can say, well, those are both equations. Well, the t-chart goes here, because what I'm saying is, here's my equation I don't know how to solve, right? In 5th grade, didn't know how to solve it. Here's the equation I don't know how to solve, but the teacher's saying to me, but is x equals 4 a solution? You don't know where that 4 came from, but is 4 a solution? Well, you take the solution, the proposed solution, and you plug it into there, right, to check. Well, that's what you have to always ask yourself here. What's my equation? And what's my proposed solution? Well, the differential equation is your equation. And this is our proposed solution. So we're going to take this y, and we're going to plug it in there. And over here, we got to plug y prime. Now, a few people I helped this morning were putting 1 over 2y on this side. They say, well, y prime is 1 over 2y. So they say, we'll substitute the y prime, put 1 over 2y. Well, then what do you got? You got 1 over 2y equals 1 over 2y. Is that going to come out equal? Every time, right? That doesn't make any sense, right? You can't say y prime is 1 over 2y and sub it over here and then say, are those 2 equal? They're always going to be equal, right? That's not what you do. For y prime, you got to go over to this. You got to say, this is y. So what I need to do is the derivative of it, using my rules. I do the derivative of it. That's my y prime. That's what I substitute over here. And then I'm trying to see if those two are equal. Sometimes it'll be yes, sometimes it'll be no. Okay? Anyway, so again, I'll have these notes up on the website. And then, okay, so chart, global max min, probably half, roughly, I don't know, I'm kind of estimating, but differential equation, like verifying a solution or working out like a bank interest problem or something like that, maybe that's another third, and then whatever's left is just kind of doing some derivatives. Anti-derivatives, very, very small piece of that, if any, okay? So whatever that leaves, another 15% or whatever of the points, a small part. Okay, and of course this is going to involve, this top one up here is going to involve both calculator and no calculator. Your work looks pretty much the same no matter what. The difference is on the no calculator, they're going to be trig values you should be able to find without a calculator. And then the calculator one will be probably some decimals and strange values that you could never find without using a calculator. Okay, all right. So that's really, and then of course, and then I'll have all the derivative rules up there again, posted up there. Okay, so try to organize it in your head there a little bit that way. So let's talk about the homework. Where do we want to start? Let's start with somewhere on that 2.5 section, one of those problems where you had to verify. Tell you what, let's start right from the beginning, because there's something with the negative. It was y prime. Tell me what problem this was. Y prime equals 1 over 2y.
Negative.
Was it negative, the very first problem? Negative. And then it asked if y equals square root c minus x. So this is very similar to the one we did, right? Very, very similar, okay? Is this a solution? So this is our proposed solution. So I'm going to come over here and do this. And I'm going to say, all right, I got to plug this into there. So this would be y equals c minus x to the 1/2. Okay, now this is where a number of people kind of got off base. I normally wouldn't do this, but I think it'll help you to see it. I'm going to just rearrange that inside. Is that the same thing, what I just did there? Isn't that the same? C minus x, negative x plus c, same thing. And if I stick a 1 right there, isn't that true too?
Yeah.
Right? Okay, you might be saying, why was he doing it? Well, we'll see in a minute here. So now I'm going to do this. And so now in place of the y, I'm going to put this, right? So that'd be negative 1x plus c all to the 1/2, right? And over here I need y prime. Where am I going to get that? By doing the derivative of this. So I'm going to bring the 1/2 down in front. We always leave the inside alone, right? To the negative 1/2. Now we have a rule that says if you're multiplying the x on the inside by something, like if it's a 2x or a 4x, what do? You kick it out. Are we multiplying the x by something in this problem? Negative 1, right? See why I wrote it that way? We're multiplying by negative 1, so we have to kick out a negative 1 on this problem. Now, a lot of people that came in this morning didn't see that. When it was written c minus x, you didn't notice that. There is a number in front multiplied times that x. Now, it's this derivative rule right here that we're using. It's this derivative rule right down here. When you're multiplying a number times x on the inside, you leave the inside alone, but you also have to kick it out. So, we have to kick out a negative 1. So I'll go ahead and multiply that with the negative 1/2. So we get negative 1/2, and then we get negative 1x plus c to the negative 1/2. Now, since that's a negative power, we'll flip it down to the bottom with that 2. And voila, we have a match. So yes, that is a solution. Then it asks, is negative square root of c minus x a solution, right? What do you get there? Turns out it is. Let's see what would be different here. You'd have a negative on this, right? So when I plug it in down here, when I plug it in for my y, what will happen to that negative? If I have a negative in front of this, and I put it down here, on negative over negative, which is positive. So this will look exactly the same, except it'll be positive, right? And then when I do my derivative, I'll have a negative out here. So when I bring my 1/2 down in front, this will be negative. But then I'll have to kick out that -1. And the negative times the negative will be positive. So when I put it over here, this will be positive. So what will happen? Both sides will be positive. So will they be equal? Yes. So it turns out there are two solutions. Just like in some equations, like quadratics and stuff, we have more than one solution. So it turns out this is a solution, and negative square root of that is a solution. Yes?
Does the -1 distribute to the -1/2 power?
No.
No. So then how is it?
Oh, wait, time out. What did I do wrong?
I don't know.
Anybody, what I have wrong? I'm guessing you noticed that.
I have to do that as a negative.
Once I move this down to the bottom, I made my eraser so small. That should have been positive 1/2. But anyway, I don't know, is that what you were thinking of? Or is that what, yeah. When I moved it, when I flipped this to the bottom, yes, that, so I should have made that. Okay, I should have made that positive. Okay, so there's, yeah. That was a mistake. Okay, so anyway, there were two solutions there. All right, let's pick one of the other ones out there that you had where you had, there's a whole bunch of them in the homework here where you had to verify pretty much all of 2.5 was at. 25. Okay, what was 25? Clay, tell me what that said. Somebody got it handy? You got it. Y double prime
minus 4x y prime plus 4y equals 0. And then is y equals x squared.
Okay, so the proposed solution is y equals x squared. Just like x equals 4 is our proposed solution, so we stick that into the equation. So here's my differential equation right here. Remember, a differential equation is any equation that involves one or more derivatives, and the solution to a differential equation is the original function y. So what we're doing here is we're saying this function y equals, is it the solution to this differential equation? So everywhere I see a y, I'm going to plug an x squared. So right here, I'm going to plug x squared, right? And then what am I going to put for y prime?
2x.
I'm going to put the derivative 2x. So I'm going to put 2x right there. And then what am I going to put for y double prime?
2.
Y double prime would be 2. So I'm going to put a 2 right there. So I'm going to have 2 minus 8x squared plus 4x squared. And that would be 2 minus 4x squared. And then on this side I have 0. Are those equal? No. So those two sides are not equal. So when I substitute in my proposed solution, which is different than 5th grade, right? Because we're not in 5th grade, but it should be different. But when I put in 4, there's only one place to put it. I got x's in there. That's all I got. I put a 4 everywhere I see an x. But here we got y's, we got y primes, we got y double primes. Our solution is a y. So we plug stuff in for y, but we also plug its derivative in for y prime. We plug its second derivative in if there's a y double prime. Okay? So that answer is no. Anything else? See, the one we memorized, remember, the one we're supposed to, we know that y prime equals ky, right? And the solution to that is what? AE to the KT, right? So that, now that we know there's no intruder taking that on the door. Okay, we just got over to this. All right. So we've been told that this is a solution. Let's just show that it is, right? Let's just show that it is. So this is not any number. Okay, this is the differential equation number 2 that I said we just need to recognize when we see this situation. Okay, and it shouldn't surprise, I should have mentioned this yesterday, it shouldn't surprise us it's an exponential. Pretend k is a 1. Then you get y prime equals y. What's that saying? It's saying the derivative is the same as the function. Now what function did we learn that it's its own derivative? E to the x, right? E to the x. So it's not a surprise that this is what's happening on this situation here, because we've kind of already said that. But then you could have some numbers in there, and that's what the k and the a end up being. So let's just do it. So k, and then we'll put in place of y, we'll put a e to the kt, right? And now for y prime, we do the derivative of this. Well, what's the derivative? Well, let's look at it. A is just a number out in front, right? So it just hangs out. Now we're doing the derivative of that. Well, E is its own derivative. What's the inside here? The KT is the inside, right? T's the variable. K's just a number. A's just a number, right? So that's the inside. So E is its own derivative. So we leave the inside alone. It always stays the same. And any number that's multiplied by the x, which in this case is a t, any number that's multiplied by it, what happens? We kick it out. So this would be a e to the kt, and then with a k kicked out. Now those two the same. Right? I mean, it's just the k's over here instead of around front. It's right. So they are the same. So we've just verified that, yep, this thing I told you was a solution is it. Now, we don't know where it came from. It makes sense that it is. We verified that it is, but we have no idea how to solve this. If I just gave you y prime equals ky or one of these difference equations, we wouldn't know how to get the y, right? The only ones we know how to do that on would be the very simplest ones. If I give you y prime equals 6x minus 5, and we're not good at it yet because we really haven't done it, but if I give you y prime equals 6x minus 5, it's got the x in it instead of a y, right? When it's got a y, we can't do an antiderivative because it's with respect to x when we do derivatives and antiderivative, or t, or whatever the input is. Well, here we can do that. We can say, hey, we know that'll raise up to a 2, so it'll be 3x squared minus 5x plus c. We can check it, right? Those are the only ones we can truly solve and find the original function y. The solution to a differential equation is the original function y. To go from y prime to y might involve an antiderivative. Those are the most basic kind, okay? Otherwise, we can't really solve them. So right now, we're just focused on verifying that something is a solution, okay? And why mess with it now? Well, because it allows us to practice. Part of doing it is we have to do derivatives. We have to learn our derivative rules, and that's our main focus right now, is learning our derivative rules. So we have to do our derivative there, we have to do a derivative there, right, in this process. Okay, so let's move on to, how about the bank interest one? Was it 47? They said P prime equals, didn't they give you that? 0.08P, right? Okay, now does that look familiar? Isn't that y prime equals ky, right? Except the y, our output variable, is not y, in this one it's p, right? So it's P prime equals 0.08P. So the solution to this should be P equals A, E, and instead of K, this is the K, right? And so 0.08 and then T, right? Again, we said we're memorizing that as a solution. So if we're memorizing it, we got to recognize it, right? We got to recognize it. Now, it should be easy. It's the only one we know. It's the only one we know for this quiz. Exponential, the exponential. And if the problem involves something about a bank and money interest, this is what it is. It's exponential. Or population and population growth, this is what it is, right? I mean, that's it. That's all we're doing on this quiz when it comes to these differential equations. If it's a bank or some kind of growth, it's this, AE to the KT, okay? Now, the advantage, and it might be written, somebody asked me that this morning, well, is this different if they write it P of T instead of P? No, same thing, same thing. When we write y equals x squared, we could write y of x equals x squared. It's a function. That's the same thing. We usually don't, just because it's messier and it's just more notation, so we don't have to, okay? So what do they say in that problem? They said you put in 2,000 initially. So what does that mean? That's your A. Now, I would say you want to be a little careful on that, some people just say, oh, the initial is always A. Well, yeah, but let's understand why. P is the principal. P is the amount in the bank. So technically, the P is the 2,000. And the little t is time. And when you first put it in, what's the time? 0. So then what happens? You have e to the 0, which is 1 times a. So you have a equals. So that's why the a is 2,000, right? So you want to be a little careful and make sure. I mean, sometimes, not that it'd be a big deal, but what if the problem was worded this way? A person put in $2,000 when they were 10 years old, and what was it? They wanted to know 10 years later?
Yeah.
So what if the problem was somebody put in $2,000 when they're 10 years old, and how much is there when they're 20?
You put a 10 in for T.
See, what I would do is I would use when they're 10 years old, I would call that times 0, right? If you call that always times 0, the beginning amount, then yes, the A would be 2,000. And then you would put a 10 in for T, not a 20, right? Because when they go from 10 to 20 years old, that's 10 years. The mistake would be putting a 2,000 in for A and then putting a 20 in for T. See, because that'd be a 20-year period. So you do have to be a little careful. So that problem I just was telling you, there'd be two ways to do it. You could go, okay, I put in 2,000 when the person is 10 years old, right? And you could solve for A that way, and then redo the equation and then put a 20 in, and you get the same answer. So it's up to you how you do that, right? But I agree. I would probably, if the person put it in when they're 10 and took it out when they're 20, I would just call the first number 0 and then the next number 10 later on. All right. Anyway, so the equation then becomes P equals 2,000 e to the 0.08 t, and this would clearly be a calculator problem. Now you put a 10 in, and what would it come out to? 4,450 or whatever. Okay. Now, and this problem points out something about differential equations. The solution to the differential equation is the useful function. This is not useful, right? I want to know how much money I have in 10 years. I can't plug into this. All this tells me is how fast my money's growing. It doesn't tell me how much I have. That's what I want to know. So the solution to the differential equation is the more useful thing. That's why we're interested in finding them. Okay? Because then we can plug numbers into them. Okay, so that was what you were supposed to do on 47. All right, that's probably enough of that, and then give you some practice time here in a little bit. So now let's talk about the max min problem. Let's do the calculator one. Let's do 44. Okay? And if you need some help on 37, 37 was a lot like the one we did yesterday, wasn't it? Very, very simple. Okay, so was it 44 we did with the calculator? Okay, and oh shoot, I forgot to get the hats. All right.
It's okay. Yeah, that's fine. We don't count.
Okay, Akshay's the presenter.
Oh no.
Good job, Ed. All right. Good thing you caught that, because whoever it landed closest to, if it broke, was good. I never would have done that a few years ago, but they seem to be pretty sturdy. So. All right. All right, very good. Boy, he got that up in a hurry. All right, good job. All right, Emily, tell me what the equation was.
Okay, I'm on the page. Okay, 44.
Yep.
Okay, f of x equals 2 cosine of x plus sine of 2x.
Now, here's how you can tell right away that this is not going to be a no calculator one, because sine of 2x and cosine of x, I mean, that's going to be a mess. And to be able to solve and, having a different thing on the inside, and it's just not going to be a nice, easy one like cosine equals 1/2. But those are the kind we would do without a calculator. The pi 6, pi thirds, pi fourths, those kind of things. Okay, So there it is. Now, since we're using our calculator, here's what this needs to look like. And this is what I really want to talk to you about, because the reason that half the points on the quiz come from this is because you get a point like at every step along the way in these problems. Okay, and you've got to have it on your paper, even though this is a calculator, because you might be tempted to say, oh, I could just go graph that thing. And what did this question ask? 44 asked all kinds of questions. Stationary points, decreasing, max min on C. What kind of max min are they asking about there? That's global. Usually, if they don't say local, it means global. When they say find the max and min values, I mean, just read that. That means they want the highest and lowest points. So they're talking global there. Okay? And then they want to know concavity, which means we're going to need what? F double prime. Concavity means the second derivative. Okay? So you might look at this, to be honest, you could be tempted to just graph this F graph, and you could find and then do a zoom fit between what, 0 and pi? You could do a zoom fit between 0 and pi, and you could see right away the high and low points. You could trace right to them. You could probably find the inflection points. The calculator will do that. It'll do all that stuff. But then you're not learning any calculus, right? So you could do that, but if it were me on the quiz, I wouldn't take time doing it, because it would verify for me I'm getting the right answer. So if you have time, at the end you might do it. But that's totally up to you, I guess. But it's not really going to do you any good, and you're not going to get points for it if you don't have the supporting work. If you have the right answers, but your work doesn't support those answers, it's not going to do you any good. Okay? So, what I would probably do on a problem like this, where I get to use my calculator and know I'm going to do some derivatives, is I would define the function, to be honest with you. I would probably go to Menu and Actions and define. I wouldn't have to do this, and then I would call it f of x. So f parentheses x, and then type it in. Now again, you wouldn't have to do any of this. So go ahead, and then what was it again? It was equals, there you go, 2 cosine plus 2 cosine x plus sine 2x. And hit enter. Now the other thing you could do is you could have went into your graph screen and put this under F1, and then it would have been defined as F1 of x, and then you could have called it by doing F1 of x on this screen, right? So that's another way to have defined it, okay? So however you want to is fine. Now, what do we need to do right now? We need to do the derivative, set it equal to 0. First question is stationary points, right? So, on his calculator, he could just let the calculator do that. Now, I'm going to go ahead and just do it on my page here. So, go ahead and do it. I actually have the calculator. Cosine, the rest of you, what's the derivative? You know how to do derivative? Oh, okay. It's next to the none.
Oh, it's not.
There you go. It's a thing next to the none. Well, that's good. You just do it without the calculator, because we should be able to. I'm going to give you one you should be able to. What's the derivative of cosine? So it's negative, right? But see, that's why if I was using calculator, I might just use it, because what if I forget a negative, right? I hate to miss a bunch on this problem because I did something silly like that. So, all right, plus, and then what's the derivative of sine?
2 sine.
We're going to have to kick out.
2 cosine.
Right, we're going to have to kick out that 2. So 2 cosine 2x. And don't forget to put equals 0 here. I hate it when I have to take off 1 point there, because you did not do that. You've got to tell what you're doing here. Okay, you've got to have that on your paper. All right, so he went ahead and did his derivative. Now notice how it wrote it backwards. I don't know, it's fine. When I did it, it came out negative 2 sine plus 2 cosine 2x, right? Calculator flipped them around. Whatever, it doesn't matter. You know, when I'm grading the quiz, I'm like, oh, they must use a calculator. I don't care. Why let you use a calculator, right? No problem. All right, so we did that. Now, what are we supposed to do next? Set it equal to 0 and solve. Now, on here, I have no choice. I can't solve that with all that stuff. I can't do it. So, we go to here. So, we go to algebra. We go to solve. We can arrow up and grab this, because I don't want to. That's why I defined it. I don't want to type it any more than I have to. Okay? I'm going to go up and grab that. Oh, by the way, notice what he did here. I'm sorry. what I would have done here, since I defined it, I would have just done f of x, right? In the parentheses, I'd have done derivative and then just done f of x. But whatever, it doesn't matter. It's okay to do it. So, but what I'm thinking, the reason I defined it, the main reason I defined it is what am I have to do later when I do global max and min?
Plug it back in.
Plug it back into the original f, right? So I've got it defined as f, so now I can just go f of, and I can just do it. Yes? You gotta do f. F, yeah, when we say f of x, right? Yeah, put the parentheses around. All right. So now, I'm glad Akshay has not hit enter. He did. Okay. Now he's getting all these. What's kind of interesting? Oh, you didn't get any. A lot of times you get the plus pi n kind of stuff. You got a whole bunch of different answers, but we're only going from 0 to pi, right? A lot of times when you do a sine cosine problem, you're going to get this plus n1, n2 pi weird business, right? That's because we didn't tell it to only look between 0 and pi. So I think you should get in the habit of doing that. So arrow back up to your solve. And what do we do here? We did this right at the end yesterday. We do the vertical bar. Now remember, the vertical bar goes outside of the solve parentheses, right? We're doing the solve. We do the comma x inside. But outside, we do the vertical bar, which we get by the equals, and then we go 0 less than or equal to, because I think we had square brackets under 0 and pi, right? Closed interval. So we're going to go 0 less than or equal to pi. Okay, and now we can hit enter. Nope, there's no parentheses on it or anything. Your solve is already closed. You put that on the outside of the close, or the parentheses, and there we go. So we got 0.52. Now let's go 3 decimal places. So 0.524. And what else? Is there just 2?
Yep.
What's the other one?
2.617.
Okay. Now later, when I put those into F, I'm probably going to want to put more than that. I would do 5 or 6 decimals because remember, your final answer always has to be 3 decimal place accurate. If you round early in the problem and use that later, your final answer may not be as accurate as you want. Okay, so be careful there. But for right now, for my stationary point answers, I can just give this. So that's the answer to part A right there. Those are my stationary points. Okay, now what was the next question? Where is F decreasing? So what do we need? We need a number line. So we're going to do our number line. We're going to label it F prime. We're going to put a 0.524 on it. We're going to put a 2.617. And now I need some numbers in between. So let's do, say, a 0. Let's do a 1. And let's do a 3. So we're going to take a 0, 1, and 3, and we're going to plug them where?
Into the original equation.
No.
F
Yeah, prime, right? And this is part of the deal. We got to think, where do we plug it? How do we remember that? Well, we got to understand, we got to think about what we're trying to find. We're trying to find when F prime, that's why I label it, because that helps remind me to plug it into F prime. But we're trying to find when F prime is positive or negative. So we plug into F prime to see if it is. So here's F prime right here. Now I have it up on my calculator, right? Now I didn't define that as F or anything. Now, no, it's not a solve. It's not a solve. Now this is important. We understand this, okay? This is something I always had to get my algebra kids used to as well. So if I give you a problem like this, compared to this, right? This is an equation. What do we do with equations? No. What do we do with equations? We solve them. They have 2 sides, and we're trying to make what value makes those equal. What is this called? That's not an equation. That's an expression. That's an expression. And we're trying, and we find values. We evaluate expressions. We find that. That's what we're doing right now. We're evaluating F prime at 0 and at 1 and at 3. So we're plugging in a 0, a 1, and 3. So we're not doing a solve. So what we want to do is we want to go up and grab our F prime, which was that it right there. We hit enter. This happens all the time. people go and they solve the f prime. That's not what we're doing. Now we did that, right? When did we use f prime in an equation? Well, we set it equal to 0. We solved f prime equals 0 and found those x values. But now we're wanting to take this expression and plug in a 0. Now you could do what he's doing, which is fine. But what else could we have done then? I showed you yesterday. You could go out to the end of the expression, put a vertical bar, and put x equals 0, right? But you could do what he's doing, and then every time grab it and put those numbers in. But if you got like 4 x's, you have to type it in 4 times. This just lets you type it in once. But I don't care. It's not a race, right? Just do what you understand. Do what you understand. Some people just type it in every single time. Whatever. That's fine. Okay? All right, so he did that. He put in a 0. Got a 2. Okay, now he's going to go up and put in a 1. Right? So go up and grab that. You can do the vertical bar this time. Okay? So he's going to put the vertical bar in, and he's going to go x equals 1. And he got that, which is fine. You do that most of the time. You'll say, whoops, I should have done what? Control enter, right? Should hit control enter. So we got a positive the first time. Now we got a negative. Now he's going to go up and grab that thing again. And this time, instead of a 1, or just could have grabbed the one that had the x equals already. It's okay, actually. I told him ahead of time to make a lot of mistakes to help everybody else. Normally he would not be doing it. Okay, positive, negative, positive. Positive, negative, positive. Right? So, back here, positive, negative, positive. Right? Now, if you really wanted to go to a lot of work, you could probably do the f prime graph. Could have graphed f prime and saw that it went positive. You know what I mean? I mean, the calculator's got there's all kinds of ways to do it. And if you really understand what's happening, you should be able to do any of them. Right? I really don't want you to memorize what he's trying to do here, right? I want you to understand the concept of what you're trying to find. The calculator is just a tool to help you get those things, right? Just a tool to help you get those things. So understand what you're doing, and the calculator shouldn't be that big of an issue. All right, where is it decreasing? Between here and there, right? So you would say, with your parentheses, 0.524 to 2.617, right? Okay, what else did it say? Max min values. That's your list of candidates. So we need f of, what are my endpoints? 0. So I need f of 0. I need f of pi. I need f of 0.524. And I need f of, now 0.524 is actually it is pi 6. 0.524 is pi 6. Did your calculator give you pi 6 when you did it? No. Okay. And 2.617 is 5 pi 6, right? But it doesn't matter that you didn't know that, right? Decimal answers are just fine here. Okay? Because we have our calculators and we can plug these in. So now we need to plug those in. So I would go back to my calculator and I define this. We defined this as f already, right? We defined our original function as f, so now he can do f of 0. Okay? He can do f of pi. Probably hit control enter because we're wanting to compare these, right? To see what's bigger, what's smaller. So decimals would be better, I think. Okay? Now we got to put in those other numbers. Now arrow up. Here's where we don't want to just put 0.524, right? So arrow up and let's find those values. 523, 598. Let's do that. 523, 598, just to be safe. 523, 598. There we go. And then f of whatever that other one was, 2 point. Okay. So if you're having any calculator issues, come see me, right? Or see somebody, get help from somebody. Make sure you can do this. Okay, now there's your 4 values. Now we should write those down. Okay, so what was this one? 2? -2, We only need 3 decimal places. What do you got?
598.
598? And negative 2.598? And so which one's the biggest? That one, and this one's the littlest? So now, very important that you give me what the question asked. Usually with global max min, it wants the outputs, the y values. It doesn't want the 0.524, and it doesn't want the 2.617. Now sometimes you get problems that says give both coordinates. And did 37 say that in the directions? Did 37 say give both coordinates? Don't worry about that. I'm not going to ask you to do that. With local max and min, those kind of things, we usually give the x value. Where are the local max min? Where is it increasing, decreasing? Where are the inflection points? We give the x value. Global max min is typically what is the max value. So it wants the y value, the output. Okay, so that's what we would give for that one. And then what was D? Where is it concave up? So we need F double prime. So let's do that real quick. So on our calculator, if this was a no calculator, we would just do the second derivative right now. We'll go ahead and do the derivative. Let me show you how you can do this real quick. Look where he's at. See how he grabbed the second derivative? Did you do that on purpose? Good job, Akshay. Way to go. Because we already have F defined, right? We could have done the derivative of the derivative because we had it up there. But he already had F of X defined, so he just went right to second derivative. I'm going to write that down. Negative 4 sine 2x. What else was it? Minus 2 cosine x. And now we want to set that equal to 0. So we get our calculator now. We're going to do it. Now it's a solve, right? Now we're doing a solve. We're going to set that equal to 0, comma x. We're going to limit it. We're going to go outside the parentheses, do the vertical bar. We're going to set it from 0 to pi. Oops, need an x in there. 0 less than or equal to x less than or equal to pi. Okay, and we only get 1, pi halves. Okay, we get x equals pi halves. That's a possible inflection point. What do we do with that information? We put in on a number line. Pi halves. Now we have a calculator. We could do like pi 6 or something, but why not just do numbers? Pi halves is 1.57, so I could put a 1, I could put a 2, right? Pi halves is 1.57 something. So you could plug in a pi 6 and then 5 pi 6 or whatever, something on either side of pi halves. But since we got a calculator, I typically would just go with those kind of numbers. So now he's going to do, yes, now it's an expression. This is not a solve. So we're going to take our second derivative. We're going to plug in a 1. You're probably going to have to control in there. Yeah, that's okay. So we got a negative. And then he's going to arrow up and grab that or not. And vertical bar. There you go. He's going to put in 2. It's all right. Negative, and then we got a positive. So that is an inflection point, but the question was, where is F concave up? From? Pi halves to where? Pi. Oh, usually on these questions we don't include the endpoints. On the increasing, decreasing, concave up, concave down, we usually do not include the endpoint. Not a big deal if you do. Pi halves to pi. Concave up. Concave up, right? There you go. That's it. That's it. I mean, right there with that information, with F prime number line, F double prime number, we know every single thing that's in the chart. We know local maxes and mins. We know inflection points. We know concave up, concave down, increasing, decreasing. It's all there. And then we add in the global max min piece, which is the list of candidates. Because we got to plug those into the original. Remember, it's the stationary points and the end points are the only places a max and min should be. A global max and min. Because of this picture right here, right? It might be at the ends, but it might be at a place where the derivative is 0. Okay, there you go. If you can verify, yeah, we should do the quiz right now. If you can verify a differential equation, and if you can do a problem like this, if you can do a problem like this with the number lines and the list of candidates, you're gonna be in really good shape for that. And we'll touch on some other stuff. So the next line, I wanna give you time to work here and ask me other questions and check your answers in the back and all that good stuff. So the next line, some of you have already done that, right, Jared? Maybe, but now you can go back and do it.
Actually do it.
You can go back and actually do it. Okay, so the next line, which says, starts with 2.5, where it says number 23, number 24, it says 48, A, B, C, and E, number 49, right? I think that's exactly what I want you to do. Now, again, when you see the part that says 2.7, 41, and 45, 41 is a no calculator. 45 is a calculator, very much like 44 was. So again, you get good practice, and you've got a good template to look at here on how to do it. Okay? There you go. All right, here's the answer book if you want to be looking at those a little bit. Want to work together, ask me. Yes. No, I gotta take a break. I'm tired. That's right. It's been a long week. All right, 2.5.
Here's this.
Okay, again, on 41, I think it says find both coordinates. You don't have to when you're doing the local max min kind of thing. You just
So is it 11, 14?
11, 14, and 55 on that section. Yeah. I think that's what the sheet says. Yeah. Yeah.